Okay, by this point, I hope you guys understand the basic concept of a CMake target. To reiterate, it's just a collection of properties. And now what I'm going to do is I'm going to delete the engine library, and I'm going to make it more realistic on how real game engines would work. Again, I'm obviously not going to write a very complicated game engine. This is the whole purpose of me writing a simple game engine structure, is to give you an example of how you can use CMake to build complex software. And I'm only using the game engine project structure as an example, but remember, you can use CMake for any sort of project, and basically everything that I'm going to show you will apply in your use case scenario as well, right? So maybe if you're writing a finance application, I don't know, or maybe you're writing a library which helps with compression, right? So there's many different kinds of software you can make, and yeah, you can just use this example to understand more about CMake, and you can make a build system for your software as well. Okay, so just to give you an idea of how game engines work and why, what we're gonna do, I'm just gonna quickly show you how a simple game engine works, right? So yeah, if you don't want to hear about the game engine at all, just skip to the section where we talk about CMake again, where we're actually building stuff with CMake again. But again, if you're curious, you can just watch it. I'm quickly gonna talk about what happens in a game engine, right? Okay, so when everything is compiled and you have the game application ready, and when you open it and when the game runs, it usually goes through three different phases. I'm gonna talk about them now. The way you write them as a game engine developer, or maybe the game developer, you write the code in you write your code in many different ways. But at the end of the day, lots of game engines, or lots of game applications, they go through these three phases, which is the first phase is the init phase, where you init all your objects, you init all your singletons, maybe the application and the graphics object, right? These are just container classes. So if you don't know what a singleton is a single instance object that normally lives through the entire lifecycle of the application, unless you choose to destroy it at some point. But usually all the big ones, like application, graphics, they're all containers that are created at the beginning of the program in the init phase, and they're destroyed in the cleanup phase, right? I'm going to get to the cleanup phase soon. But so they are containers which contain all the related objects. Like the application will have application will have member variables that hold some data about the application itself, like how big the window should be, how what kind of renderer do you want to use? Do you want to use what kind of API do you want to use for rendering, right? And okay, maybe the graphics class will have all that rendering information, and so you get the idea, right? So initialize all the singletons here on the engine side, and on the game side, you can let the game developer initialize all the game objects. Like maybe they have so maybe they want to spawn some objects when the game begins, and so that they have things on screen, and the player, maybe it's a third-person game, maybe the player has to be present on the screen, so that it has to load the player and load the environment around him, and things like that, right? The game developer will instantiate all the objects that are necessary for the game, things like that, right? So because I've been writing my 3D game engine, I only have idea about how 3D game engines work. So usually after the singletons are initialized on the engine side, what happens is you usually have some sort of a loader which loads 3D models. Normally people use 3D modeling softwares like Blender or 3ds Max or Maya or whatever for modeling things, like making 3D models. Like for example, you make a cube, sphere, and a cone, and maybe you have some lights here, some point lights, maybe a sunlight, and maybe a camera, right? So there's multiple objects you can make in a game, in a 3D modeling software. And what you do is you export all of this information into a file, right? Like a GLTF file or an OBJ file. All these are really popular formats, and you take the file location and you send it to the loader, and the loader will parse it, and it will make all the information that's in the GLTF file, and it will parse that, and it will make a scene normally, or scenes, right? So this whole entire thing is a scene, right? What does a scene contain? A scene is usually like a tree structure, which has let's say this is a scene object. It has information about hey, how many objects that this scene has, right? It has meshes, right? Meshes, and it has lights. It has cameras, if there are multiple cameras, right? And all the meshes are right here, like mesh 1, mesh 2, mesh 3, which is cube, or the cone, and sphere and whatever, all the meshes that are here, and the lights similarly, and the camera, all the cameras here. And right, if the cube is kind of parented to some other object, maybe there's another cube here, sorry, maybe there's another sphere here, maybe there's a couple of spheres that are parented to the cube, right? So all these can be linked or parented in a tree structure to the cube, like sphere 1, sphere 2, sphere 3, right? Sphere 1, 2, 3. All these can be parented, so all the information is tightly is linked to the object that it's parented to, right? So this information is normally in a scene. It's all encoded in the GLTF as well, but it usually has all the information about the scene, right? So so what you do with this information is up to you. So that's what you do when you parse the scene through a loader, and you can parse the scene and get the information and create your own scene object in your application. You can create like objects that are necessary. You can interpret this information however you like. And yeah, you make the scenes, you initialize the graphics context as well, right? So you initialize all the renderers, like maybe you have two renderers in your game engine, maybe like one OpenGL renderer and a Vulkan renderer. You initialize that here, and then you make the render passes, right? Like what happens. So when a game engine draws things on screen, it usually needs information about passes. Like think of it like painting, right? When you start a painting, you clear color, like you clear the canvas with some sort of like some base color, and then you apply another layer of like the background, maybe like the sky. You want to paint it blue first, and then for the ground you want to paint green. Yeah, so you apply some base layers, and then you build layer by layer, right? So similarly, you can make these layers like in the game engine as well, and these are normally called render passes. Like each pass will do one thing, will describe the information about how to paint and what kind of canvas to use. In this case, there's just like formats, and yeah, so it's very specific to game engines. But yeah, so that's how you do, like you init your render passes, create like frame buffers, which is analogous to making a canvas paper in the painting world. Yeah. So yeah, you init all these objects, and then you go through the game loop phase where you have a condition like this, like while you want to wait until the window is closed, right? Is window closed? No. If it's not closed, then like keep coming back, keep looping back, right? So that's what basically it is. Like you're stuck in this loop until the user gives a signal. In this case, like if the user says if the user clicks on close window, until then this loop keeps running, right? And this is usually called the game loop. And inside this, you kind of use all the information here and provide a way for the game developer to update all the information that's in the game loop phase, right? So maybe like they want this cube to drop on the floor. Maybe there's a plane object, and they want the cube to drop on the floor. So when they like update, when you provide them with the on update function or callback, whatever, right? You provide them a way to like update all the things in the screen. So in frame 1, maybe the cube is in a different position, and in frame like 10, it should like drop on the floor, right? Maybe they want to capture some event, like, right? If somebody clicks the keyboard, they want the cube to drop down, they can do all that in the all on update function. And then finally, they have like a render phase. This is the main part of like the game engine, where they take all the information that's available and they can render it, like they can paint all that information on the screen, right? How does it happen? It usually, like, all the scenes are first saved like in the CPU memory, or like in the RAM memory or whatever, and then all the static data is saved in the like vertex buffers or the index buffers of the 3D model information that's really large. They're all saved in static buffers in the VRAM, like in the graphics card memory. And then once you save all that information in the graphics card memory, you use that information to render, right? And sometimes you want to update things that are really small. On the update side, like the game developer mentioned, like, hey, on the update, just like blink this light, right? So the light's brightness changes from 100 to 0, and then from 0 to 100, like in a span of like I don't know, like 100 frames, whatever, right? So you can just like let the game developer update that information here. And on the game engine side, what you can do is like you can interpret that information, and you can change the values and and you can like copy them into the graphics card, like usually like in dynamic buffers, and you can just like at the end you can just render the scene, like whatever, right? So yeah, so this is what happens in the game loop phase. There's many things that happen, but just to give you like a simple overview on what happens. And finally, after the game loop ends, maybe the user gave a signal to close the window, or maybe like when they hit, there's a button called quit game in the menu of the game, UI of the game, and then when they click that, they will it will exit this loop, this while loop, and then it will go to the next instruction, which is like cleanup. Usually what happens is like it destroys all these objects that are created in the init phase by running all of their destructors, application dot destroy, right? If it's a singleton, there's a, yeah, so it just destroys the object and it cleans up things, right? So this is a very simple way to like describe what happens in a game engine, right? Okay, so I'm gonna make some classes now. I'm gonna make some code, and then we're gonna make some libraries, internal libraries, and then we're gonna connect them and give the game developer a very good way to like use the game engine, right? So yeah, let's start doing some code right now. All right, so let's go back to the code, and I'm actually gonna delete this engine library, and I'm gonna rewrite it again. So what I'm gonna do is I'm gonna create some of the things that I described earlier just now. So I'm gonna write some singletons. I'm gonna write the application, the graphics, and something called a renderer. And I'm gonna link these libraries to show you how you can use these concepts and make like a meta build system with CMake, right? Like, okay, so let's go back and let me create. It's really hard to describe it verbally, but as I'm doing through the code, you will understand things much better, like when it comes to like making build systems. So let me quickly create the folder for the engine stuff. This time I want to give my engine an actual name. I'm just going to name my engine Coffee, right? Because I cannot think of any other name. So my engine is called Popcorn, and so yeah, I'm terrible with names, right? I'm just going to call it Coffee, and then it's going to have an include folder, and it's going to have a source folder, right? It's going to have a source folder, right? So the include folder will have all the header files, and the source folder will have all the CPP files. So the thing is like there's no actual rule that it has to follow a certain structure, but the convention usually is like to have a source at least, right? And I like to have include folder separate, but lots of people, they tend to like put all the header files and the implementation files in the same folder just so they can open it with their like file editor. Like because they're side by side, you can just open them whenever you want. But I don't like to do that. The reason is like I like to put all the include stuff here, and when we're installing, we can just install all the stuff that's inside the include folder into the system folders. So when we specify the include command in CMake, like I showed you, you can specify some of the base directories in file sets, and you can use that base directory information that you associated with the file set inside the install command, right? So for the install target, you can when you mention the file set, it will take into account all the base directories that has all the header files, and it will just copy all of them at once into the system folders or whatever, right? So that's the reason why I have here. Again, if this doesn't make sense, don't worry. I'm going to demonstrate it practically. So let's write some include files. Okay, so in the include folder, I'm going to make another folder called Coffee. I know it's kind of weird, right? Like the engine project is Coffee, and then inside the include folder, we have another folder called Coffee, right? Why? Because when I'm installing stuff, when I give the installation command, what it does, it's like, as I mentioned, it's just going to copy files that are inside the include folder into the system folders. If I hadn't made a different folder called Coffee and then put everything inside it, it will copy all the files directly. And if there's an existing file that whose name clashes with mine, it's going to be a problem, right? So the system won't know which, I mean, it can know with paths, but it's not a clean way of doing things, right? So it's better to put everything inside a Coffee folder. So CMake can just copy that Coffee folder into the system directories, and everything associated with the Coffee engine is still inside that one folder, right? All right, so we have the Coffee folder, and I'm gonna make something called core, because I'm gonna have all the core classes here, like application or window or like things like that, okay? Coffee, and then I'm gonna have another folder called graphics. I'm gonna put all the graphics stuff here, right? And I can actually have another folder called renderer, but I can put that in the graphics folder itself. Let me create another folder, renderer. Okay, I'm gonna copy all these files to the source as well. Sorry, folders to the source as well. And okay, so we got the include files and we got the source files, and now I'm gonna create the CML file here, CMake lists, right? cm.txt, and I'm actually gonna copy everything that's here into this CML file regarding the project information. right? Except it's not called the game app, it's called coffee. You can name it whatever you want. Coffee project, coffee engine, or yeah, coffee project, all right? Okay, now what I'm gonna do is like, I'm gonna add subdirectory and put in source folder here. Okay, so let me explain about add subdirectory, right? If you remember what I told you, whatever you specify here, whatever folder you specify here, it's gonna go into that folder and it's gonna look for a CML file. It's basically like include, hash include, where it, if you specify a hash include a header file, it will basically copy all the contents from the header file into the current file that you're including the file in, right? So similarly, it will look for a CML file and it will include all the information that's in the CML file here. So basically, that's how I can just like use sort of like module system to not pollute this base CML file. Sorry, to not pollute this base CML file with all the information that I want to specify about this project. That's basically why I'm doing add subdirectory, and all the build information about the source directory, like whatever is inside the source directory, I'd like to have another CML file that deals with all that. So I'm going to create another CML file. .txt, right? So this one has its own CML file, right? So, and this main CML file accesses that CML file through add subdirectory. Yeah. All right. So let's open this now, and I want to have another CML file inside core. I want to have another CML file inside graphics, and I want to have another one inside renderer as well, right? So the reason I'm doing this in such a deeply nested way is because as the project grows, there's going to be lots and lots of files, and I like to have the library specific information. Like I'm going to turn some of the files inside the core into an actual static library, and then finally I'm going to link that to my engine library. And so that's why I like to have all the library specific information inside that folder. And so that's why I'll create another file called cmakelist.txt inside the core, and I'm going to do that. I'm going to paste that here as well. Yeah, so I'm going to have separate files here, and this way it's clean. This CML file will only have the information about core, and this one will only have information about graphics. This one will only have information about render, right? So in this CML file, I'm going to mention that I have all of these files, all of these folders, and it will look for CML file inside core, graphics, and renderer, right? Okay, so it did all that, and now let's actually write some C++ files, right? Because I wanna make some targets now. Okay, so let me close all of these, and let me create some classes, right? Let me create application.cpp, and in here I want to add a file called graphics.cpp, and here I want to add a file called renderer.cpp, right? And let me create the corresponding header files as well. Application.h and graphics.h and renderer.h. Okay, so all right, so now what I want to do is like I want to specify the core information here. Okay, so let's make these libraries now. I'm going to create the core library first. I'm going to make it static. So again, this command add library, add underscore library will create a library, and we need to specify the target's name. In this case, our target is a static library. So the library's name is core, and the type of the library is static, right? Okay, let me actually like talk about all these commands that we've been using, because until this point, I've only showed you all the various commands and how you can use them to like make a build system and then eventually build the files, like build all the libraries and like targets and stuff like that, and then how you can use them to install. But I've never actually talked about the commands itself, like about the CMake commands itself. And yeah, so let's do that right now. Okay, so the way we added the library is by using the command called add library. And if you look at the CMake documentation, let's go back to the CMake documentation and let's look at the CMake commands. I'm going to search for add underscore library, right? If you open that, and you can see, like, you can read the documentation for this. So all the commands that I'm showing you here, it's worth spending some time to read about them, because they're very commonly used, and they're also used in third-party libraries, which we're going to get into when we progress further and we try to like install stuff like GLFW or like IMGUI or whatever external library we decide to do. Because all this stuff that I'm teaching you right now, CMake the libraries, they also use CMake, and they also use all the CMake lingo, all the terminologies that the CMake uses. And so, and when you understand all these concepts, they will be very useful for you when you try to read all the external third-party library CMake files as well, right? Because you might want to link against them, right? You might want to build them from source and then link to your link them to your target and then build everything at once, or maybe you want to build those libraries separately, and then you might want to link to them, link to the binaries instead, right? Like I showed you, like option 1 and option 2. So for that, I highly recommend you guys to like learn about these commands, all of the commands that I showed you. But anyway, let's quickly take a look at the add library now. And add library obviously makes the libraries, the different kinds of libraries. Let's take a look at that. So it creates something called normal libraries, object libraries, interface libraries, imported libraries, alias libraries, and like it's got some other stuff here, right? So let's look at normal libraries. And this is the signature for add library. It's going to take in the name of the target, and it's going to take in the type of the library. The type is usually static, shared, or module, right? Yeah, I think that's about it. So these three different types of libraries can be created, and it can also take in a flag called exclude from all, and it takes in some sources, right? It takes in some source files. Now, I don't really like to specify all the source files here, but then a lot of projects actually use this command and specify the sources right here. I used to do this before I learned like modern CMake, before I went through the tutorial. But I'm going to show it to you this way first, and then I'm going to show you my way, which is like using something called target underscore sources to describe all the information about the sources of the target, like I showed you earlier. But I'm going to dive deep into that now. Okay. All right, quickly. So let's look at the different kinds of libraries now: static library, shared library, and a module library. Okay. I'm going to quickly explain all these different kinds real quick. Okay, we have options like static library, dynamic library, or a shared library. And we have something called a module library, what CMake calls a module library. So the static libraries usually end with .a in Linux, or they end with .lib in Windows. So we already talked about these things in the previous section when we talked about like the compilation process. But this is, I think, an appropriate time for me to like explain briefly again, so that we know with the example that we're doing right now. So you understand that like really well, right? So okay, so we can create some static libraries, we can create some shared libraries like .so or .dll in Windows, and we can create some module libraries. I don't understand the extension, so I'm just gonna write xxx and yy, whatever. Anyway, so we got static libraries. Basically what it means is like when you write like a header file, let's think about like our core library, right? We're gonna be making the core library right now, by the way. We're gonna make another library called graphics as well, and we're gonna make a library called renderer as well. We're gonna be making all of these libraries, but for now let's focus on the core library. So what does core library contain? It contains like a bunch of header files, like the one that we did right now is like application.h, which contains the application singleton, and it can also contain like a window.h file. So all these are header files, and it also contains some CPP files like application.cpp and window.cpp, right? These are the files usually that they're in core, the sources we have in the core library. And what it does is like CMake, when we say like we mention all these sources with to like the target, the library's target. So what it does is like, hey, okay, it looks at application.cpp, and this has an included file, which is like it includes this header file. So what it does, it combines both, and it creates one huge CPP file, like one translation unit, which contains everything from here. If this application.h includes something else, maybe like it includes IOStream, std IOStream header as well, so it's going to include that as well. Like it includes that in this first, and then it includes the application.h into the application.cpp translation unit, right? Once it finishes the translation unit, and then it compiles the huge CPP file, and it makes something called a .o file. So the way CMake does it is like application.cpp.o. Like this file is an object file, which means it's a compiled file, but it's not linked yet. It's not linked to other targets yet. So, and it takes in these two sources as well, and it creates something like window.cpp.o, right? So this is another translation unit's object binary file, and at the end what happens is like it takes in both of these and it creates the library, right? Like the core library. So because we're in Linux, it makes something like libcore.a, right? libcore.a. This is how the whole thing works, just to recap. And we got libcore.a, right? And this libcore.a is a static library, because remember I said that .a in Linux is a static library. I mean, let me give you another example. Like instead of this library, you can link it to something like an executable, right? Like an executable which you can run directly. Like maybe our game, right? Maybe the game developer like made an executable like game, or in Windows it might be called like game.exe, right? Okay, so the game executable, if they link it to libcore.a, it will embed all the information, all the instructions, all the implementation instructions into the game as well, right? So when you open the game, it runs straight out of the box, and even without this, if someone deletes this binary, it just like runs, no problem, right? All right, so this is what a static library is, and now let's talk about the dynamic libraries, okay? Okay, similarly, they can also create shared libraries, which means that these libraries need to be present during runtime, because it works exactly the same way. Like they'll when you compile the code, it creates multiple translation units, and it will resolve all the symbols, and like it will resolve all the dependencies. Sorry, it will resolve all the dependencies, and it will see which target is linked to what, and then it will create a final library, target library. In this case, the dynamic library or a shared library, like let's say libcore.so this time, right? Or so, and in Windows, I believe it's DLL. I'm not really sure, but similar, right? So it creates this, and then when a game links to this, let's say the game, when they're compiling their game, they specify in their CMake setup that my game executable should link to this library. They will, and then they create the game executable, and when they run this game, it needs to have this file as well, because all the things that the game uses from this library, they are dynamically linked, right? So which means that during runtime, like it needs all the instructions from this file, so it needs to be there. So if you delete this file and the game kind of depends on this, so it won't run, like it will crash, right? So because it cannot find all the symbols, and like it cannot find the instructions that the game needed from importing this library's stuff, right? So that's what a dynamic library is, okay? And we finally have something called a module library. I'm not exactly sure about the extension, but typically what happens is like you can load some of the libraries in the language itself. Like you can when you're writing your C++, you can say something like I don't know, it's called DL open apparently, and you can specify where the library is, where the binary file is, and in the language, when this instruction runs, it will at runtime, it will find this library, and then it will load it during runtime, right? So I assume that this is slightly slower than the other options, but I'm not really sure. Please don't come at me in the comments. So but yeah, so let me actually kind of read about this. Yeah, so module library, a plugin that may not be linked by other targets, but may be dynamically loaded at runtime using DL open-like functionality, right? So like all the stuff can be loaded during runtime. All right, so we know about this. So, okay, it also takes something called a sources. It takes exclude from all flag, which you can read about later, but I usually like only specify the name and the type. I don't even specify the sources, but I'm gonna get into it in a bit because I like to do it with target sources instead. Anyway, so right now let's put in the sources here. I'm gonna say the source for this library is going to be application.cpp, right? Remember, this is the path. This is the path we're specifying, right? So this is a relative path, to be more specific. So when CMake tries to like do something, maybe like do the build system or like build or install, I told you, remember, it goes through 4 steps. One is the configuration stage, and it goes through the generation stage where it actually reads all the config, meaning that it reads all the CML files, and it generates the platform specific build files, build systems. And after that comes the build stage where you can like build and compile all the files using the CMake --build command. And finally, you can install using the CMake install command in the install stage, right? So there's 4 stages, right? So when CMake is doing stuff, always like when you're mentioning paths, this is like a pro tip where whenever you come across situations where you have to specify some paths or files, always be aware what happens in different stages, right? So like when CMake goes to the configuration stage, so in the configure stage, it says, oh, okay, I want to make a target called core, and it's going to be a static library, and they specified some file here, the sources here. So what I'm going to do is like I'm going to store these values, these source values as strings somewhere, right? CMake, it has to store it somewhere during the configuration stage. And when it stores it, if it stores exactly like this, it means that it stores like the relative path here, right? So by default, it stores relative to where the current CMake lists file is. So we're here, we're writing this CMake file, right? So it goes and looks like, oh, okay, I'm gonna store something like this, application. So let's say like this current CMake current source directory, and I'm gonna do application.cpp, right? So this is an actual variable. So okay, I told you that CMake is a language, right? Because build systems in real life can be really complex. CMake is actually like a full-on extensive Turing complete language. You can do things like make variables and like set values to variables, and you can make functions, you can make macros, you can also like make loops, you can make like for loops or for each loops. And the thing about CMake is that the fundamental building block of CMake is a string, right? Everything here is a string, just like how in object-oriented programming you have object as your building block, like a fundamental building block. In CMake, it's the string, like everything, all the parameters you specify, all the variables that you can set to, like they're all strings. They're either strings or a list of strings, right? So yeah, like I just wanted to mention that. And so when you mention something like this, like a path, always be aware of what's happening when CMake goes through all these stages, right? This is going to be important later, but I just wanted to like mention this. So when it goes through the configure stage, it adds this relative path to somewhere, right? Like to internally it adds it somewhere, and then it does and then it generates the build system. When it's generating the build system, it looks at the variable and it says, oh, okay, so I know that this is right here, and then it will know where the file exactly is, right? Okay, so we'll come back to this later, but yeah, anyway, so relatively I'm mentioning that, okay, this is an application.cpp, so we're right here. But when we try and compile this, we're going to run into an error because, okay, actually, you know what? I just realized that we didn't write the actual functions here. I'm quickly going to write just the application. I'm only going to write the application C++. I'm going to do pragma once, and I'm going to put a namespace here. I'm going to call it core because I'm going to make this a library. Eventually, I'll make this a core library. So you'll see like when we're using this. And I'm going to create a class real quick, and I'm going to call it an application. I'm going to make it a singleton. Like I'll do it the old-fashioned singleton way. The way I like to do a singleton is like I like to make the constructor and the destructor private, so nobody can initialize it. If you don't know what a singleton is, it's basically just a class, but it's designed in such a way that it can only be created once. So when somebody who uses this class, they want to create an instance, they can only do it once. Like during the entire run application, it can only be created once, unless they choose to, whoever creates this object, unless they choose to like destroy it, it will only be created once, right? So the way we do it is like making the constructor and destructor private, so nobody can create it because the constructor is private. The only way they can create it is like making a public method and giving them something like get, and it's gonna give them. Okay, I'm gonna write the implementation right here, and what it's gonna return is it's gonna return an instance of this class itself, and it's gonna be stored. Let's put something called s instance, right? I'm going to quickly create this member variable, and I'm going to say like s or like application pointer s instance, right? And I'm going to make this static because I want people to be able to use like this, just like this is in some other CVP or header file. What they can do is like they can do it something like this: application get, right? And when they do it, they're gonna get like auto reference app instance equals this. So this app instance right now will contain an instance of the singleton, right, of the application. So that's why I'm gonna make this static, right? So you can do that. And if I made this static, which it means that this also should be static, which I already made. And what does this say? Cannot bind to, oh, okay. So it says that I have to, because I defined a pointer, s instance is a pointer, and I'm returning application reference, so I have to convert this into a reference. I can do that by putting a asterisk like that. And you only return it if the instance exists, right? But what if it doesn't exist, right? So if it doesn't exist, if the instance doesn't exist, you create it and you say s instance equals new application. So we're creating an object on the heap, and then we're returning the pointer. We're storing that pointer here, yeah, which is like this member variable right here, static member variable right here, okay? And another thing I like to do when I'm creating a singleton is I like to delete the copy and move constructors as well, because I don't want anybody accidentally like moving my application's instance to somewhere else. So what I'm going to do is like I'm going to delete the copy constructor first. So the copy constructor, if you don't know, it looks exactly like a constructor, except it takes in a const reference of the application. And I'm going to say delete. Yeah, that's it. It's going to delete this. And like similarly, I'm going to delete the operator as well. Like, sorry, I'm going to delete the assignment as well, like the copy assignment as well. And the assignment, usually it's done by equals to symbol. So what it means is like basically if someone creates an object like this, singleton or not, and if they say application equals application, something like this, and if somebody says application app2 or app copy equals app, what it's going to do is like it's going to copy the app into this, and it's going to create a copy, which I don't want, right? And similarly, I want to delete the move constructor as well, because if somebody tries to move it, I don't want them to do that, right? The move constructor's signature is very similar to copy constructors, except it doesn't take a const reference. Instead, it takes a move R value reference. So, which is like this, right? And this is exactly the same, except this is the R value reference, right? Okay, so we've deleted the copy and move constructors as well. Well, if you've never heard of copy and move constructors and you work with C++, I highly recommend to learn about them, because they're very important in my opinion. And everything that has to do with like moving data, storing data, and like how you create member variables, and like what happens when you like create these resources, and like how you want to manage the ownership, all that stuff is like really, really important. In fact, that is why C++ is really, really powerful. And at the same time, it opens up opportunities to like shoot yourself in the foot. So this is one of the things. Like you have to think about what happens to the data when somebody tries to copy, when somebody tries to move, when somebody tries to delete, all that stuff, right? So a singleton is something that I want to be able to exist in this class itself, and I want it to be able to exist until the time it's destroyed manually, right? And so I actually now realize that I didn't really create the function destroy, and which I'm going to do right here, right? And the signature is going to, sorry, the return type is going to be void, because I don't want to return anything. Destroy, and I'm going to say delete the instance, right? But only delete it if it exists, right? If it doesn't exist, well, if it doesn't exist, you can probably like do like throw an error, or like log it into like a file or something. Basically, let the user know, whoever is using this, that when you try to destroy it, the instance actually doesn't exist. It's empty. Yeah, that's what basically it is, right? Okay, so we created the header file here. I basically want to do the same. I want to like do the implementation as well. So what I'm going to do here is like I'm going to specify the namespace first. And this is also going to be the core namespace. And I'm going to say, oh, wait, this application.cpp, this implementation file is going to include that file, right? Include core, sorry, coffee, which is the name of this engine, right? Because it's right here, right? Well, technically it's an include path. We're going to talk about this later, but so this coffee and then core and then application, right? So I'm going to say coffee core application application.h. It's gonna like my editor is going to complain that it's not finding that file, because what it's looking for is like, if I specify it like this, it's assuming that because I'm right here, it's assuming that there's a folder called coffee and core, and there's a file called application.h, and it thinks that it's like this, but it in fact is not like this, right? And now like if I do this, it doesn't really complain anymore, but it's not the case, right? I'm going to delete the things that I just created, but it's somewhere way over here, right? Okay, I'm going to say this again, and it's going to complain again. I'm going to put the implementations here. So like if you define static variables like member variables here, you have to initialize them in the implementations. So I'm going to do just that. I'm going to say application pointer is application and s instance is going to be null pointer, initialize it to null pointer. Well, I could actually initialize it to like new application right here, but I don't want to do that. Like, let me keep things simple, and I will probably eventually explain how that works, but I'm just gonna implement this here. And I'm actually gonna move these implementations here, and except I don't want the static keyword here, static here. Instead, it's gonna be here. Right. So these things are implemented here, and here I kind of want to delete the implementations. I'm just going to produce the I'm just going to keep the declarations, and similarly I'm going to delete the destroy methods implementation as well. So all the implementations are in the implementation file, the CPP file, and all the declarations are here in the header file. Okay, so we've created this. We'll do the same in graphics later, but back to the CMake setup now. Let's go back to like the CMake list.file, and I'm saying, okay, take the static library here, right? And when it tries to compile, well, you know what? Let's actually try and compile this, right? I'm in the coffee folder. I'm going to say CMake, and the source files are right here, and build it in a folder called build, which I don't think I've created yet. So what I'm going to do is I'm going to go up, and I'm going to create a folder called build, right? This is the build folder, and I'm going to say enter, right? All the build files I've written there, and when I try to compile, it should throw an error. I'm trying to make a point here, so please bear with me. Look at that, right? It says include blah, 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 no such file directory. It did not find it because like I told you, when it tries to make the target core, it looks for application.cpp, and it finds application.cpp, and when it goes to the file application.cpp and it tries to like compile this, it sees that, oh, okay, this guy wants me to include the header file, but it says that a header file's location is right here, but I cannot find that here, right? Because it did not find anything in this folder. So what we're going to do is like we have to specify where the include directories are, right? We have to specify the root, or we have to specify the header files locations, where the directory location of the header files, and we can do that by using target include directories, right? So we're specifying something about the target, right? So the signature is like name the target. By the way, I don't like to do it like this. I like to use target underscore sources, which is a much better way of doing this. I think maybe the modern way of doing this, because you can specify all that information, all the sources information, right in that source in that command using something called file sets, and that's really useful. And you can specify the base directories and the files, and it will automatically like detect where the files are everywhere, right? Even during the build and during installation as well. Okay, so but right now I'm just going to show you like how you can do it manually, which I see a lot of people doing, and like I don't know, like it's much more painful in my opinion, but let's still do it, right? Core, and I'm going to specify the public keyword. Right, I think this is a good time for me to talk about the public, private, and interface keywords, like the scope keywords. You're going to come across this a lot. I'm going to do that in just a minute. But again, like if I didn't know this, I'm going to go and look at the CMake reference documentation, and you can read all about this command in there. Right, okay, core public, and I'm going to say, I'm going to look at where this file is. Okay, it's here. Right, it's here, and I'm going to say go back one directly. So we're in core, so we're in the source directory right now, and we'll go back to include, and then go to coffee, and then core. This is one include directory, right? So if you mention this include directory, it's going to look for that thing right here. Oh, sorry. So because we mentioned that the whole path's right here, coffee, core, and application, we only need to specify the include directory, right? Sorry, the include directory. Right? Did I do that right? So if I come out one folder, oh, maybe I have to like do another here, up here, right? So if I do this, it's hopefully going to compile it correctly right now. So let's do this, and it built the target core, right? So if you want to take a look at the build folder, it's got something called source, and it has source core, and if you look at it, it's got a make file, and it's got libcore.a, right? And there's nothing called graphics.a, like libgraphics.a, because we haven't added that library yet, added the CML stuff for that yet, but it's got libcore.a, and it compiled successfully, right? But then instead of doing like this, there's a better way of doing this. Right now I have to talk to you about something called scope keywords. So I'm gonna have to go back to the drawing board for that.